Okay, this is the full from our project, and this is TDS testing sensor. It have a value in it. You can see it's 15.2 now. It set the water level. It's low now because it's not catch the water. We choose this one. It can either no catch and catch water too because it have IP69. And now it means the high. It means it have water in the tree. Okay, it's full of our project. Okay, this is our IoT system, and now this live have live value. Yeah, it's changed. It shows the TDS value. And now it is the water level value. The one we set it is low. It said it's no water in the tree. And then, yeah, the zero said it's high. It means it have water in the tree. Okay, next I will start our presentation. Hello everyone, this is our group presentation, and our project is IoT water quality and water level monitoring based on ESP32. Our team members are Deng Lipan, Wang Weiyang, and Fu Jing. Today we will show the design, the implementation, and the results. This slide shows our real prototype and the 3D model. We built it on a breadboard for fasting test and debugging. The key parts are ESP32, OLED screen, TDS sensor, and a no contact level sensor. This slide shows our using of sensors and the screen. The first, we use the water level sensor, and the second, we use the TDS sensor. Finally, we're using OLED display. Why we do this project, traditional checking is manual and slow. Also, it has no historical data, so we cannot see trends. And if the water is too low, pumps may run dry. If too high, it may overflow. So we need real-time sensory, remote auth, and one device for multiple data. Our primary goal is to build a stable integrity prototype. We have 4 targets. The first one tests the high-low water level using a no-contact captive sensor, but it also has the contact captivity. The second, using Wi-Fi to upload data to SimCentral's cloud. The third, measure TDS value in ppm from analog voltage. The fourth, show data locally by OLED and also output by Bluetooth for mobile debugging. This is our system flow. Input are TDS sensor and the level sensor. The brain is the ESP32. Outputs are OLED display for local reading, Bluetooth serials, Wi-Fi HTTP, and power is from 5 USB, then regulate to 3.3 voltage. We choose ESP32 because it has Wi-Fi and Bluetooth, and enough ADC and GPIO. For water level, we use XKC-Y25. No contact sensor, but also it can contact the water. So it doesn't touch water and avoid collision, but we chose it have the IP68, so it can catch the water. For water quality, we use an analog TDS sensor model to get voltage and compute ppm. For display, we use the OLED screen, which needs only SDA and SCL lens. That is the overall ideal and hardware choice. Next, Wang Weiyang will explain circuit and firewall design.
Here is our writing logic. All modules share common ground. A key engineering issue is the ESP32 ADC2 cannot work when the Wi-Fi is active. So we map our analog sensor to ADC1 pins. The TDS sensor goes to GPIO 34, and the level sensor goes to GPIO 35. OLED use I2C SDA GPIO 21. This mapping makes the system stable during Wi-Fi upload. And then in setup, we start serial 115200 for debugging. Then we start OLED at address 0x30. Then we start Bluetooth with name water monitor BT. After that, we connect to the Wi-Fi. So after power on, the device is ready for display, Bluetooth, and the cloud. And then it's for TDS. We do 3 steps. First one is noise reduction, average 20 simples. The second is convert ADC value from 0 to 4095. It's 0 to 3.3 volts, right? And third, we use a cubic polynomial formula to convert voltage to TDS ppm. If ADC rows value is over 2000, we say 4 and high, 4 or high. Otherwise, it's low. It can display in the monitor. For the IoT, we have 2 communication models. Mode 1 is Bluetooth SPP for near-field debugging. The phone receives text like TDS46 and level 4. It means the water quality TDS is 46 and the water level is 4. It's over the ADC row value is over 2000. And the mode 2 is Wi-Fi plus cloud for long-term logging. We send a HTTP GET request to SimCentral every 5 seconds. Non-blocking timer. This creates history data for chats. And then the prototype. This slide shows the full system running on the breadboard. We can see the OLED showing network status and sensor reading. This can prove the integration works. First is it's a sensor to ESP32 to display and wireless. Next, Fujin will present the test results, code validation, and the conclusion.
Hello, my name is Fujin, and this part I will introduce the local interface of the results. This slide shows our local outputs. On LED, we show net stats, BT stats, TDS, ppm, and water level. On Bluetooth, we stream data in real time. When we change water level, the status switch between full and low. So local monitoring and debugging are both working. And next, our cloud for water level monitoring. On the blue, we mean that 1 is full and 0 means low. So on the graphs, we can see it jumps between 1 and 0 clearly. This means our cloud updating is correct and reliable. And next, for the water quality, this is the TDS chart on the Synth Central. With the volume change over time, so we can see the trend, not only one reading. This is useful for smart home or agriculture monitoring. And next, we have to accept that our project has many limitations. First, our level sensor gives only 2 states, not exact height. And second, TDS may need calibration and temperature compensation for higher accuracy. And in future, we can add a temperature sensor and use MQTT for two-way control. Also, we can design a PCB to make it more stable and for long-time use. And next, for the conclusion, we have successfully achieved our objective, and we integrated TDS sensor and level sensors on one ESP32 system. We built a full pipeline from sensor to OLED to Bluetooth and to cloud. It is low cost and reliable, and is a good base for smart monitoring system. Thank you.